Hello, Ray. Today we're going to talk about astronomy in the Renaissance and how we shifted from a geocentric model of the universe with the Earth at the center to a heliocentric model where the Earth is orbiting the Sun. So today we're going to focus in on Copernicus, Galileo, and Kepler, and maybe a couple of other characters along the way. So let's start with Copernicus. He was around, he was born in the 15th century. And he basically went back to these ideas that came from some of the ancient Greeks, Aristarchus, Pythagoras, that the sun should be in the center and that the Earth should be orbiting. Now, this was definitely revolutionary, but it wasn't adopted right away. It was something that took a long time to be adopted. And there were a couple of reasons for that. One is that in his model, yes, the sun is in the center, but the Earth and all the other planets are moving in perfectly circular orbits with constant motion. So circular motion, they are perfect circles, and uniform motion means they're moving at constant speed. And so one of the problems was that this model, although it was much simpler and preferable to some of the models that had gone before, it was still not that great at predicting where a planet should be because it didn't quite get it right. But it really laid the groundwork for what came next. So what came next? Well, I think everybody's heard of Galileo Galilei. He was one of the first sort of public scientists. He was someone who, instead of writing in Latin just for those people who were erudite, the people who could actually understand Latin, he wrote in Italian for the general public. And so that made him both popular with the public and unpopular with, for instance, the Pope. And he used comedy in the way that he presented his ideas. Now, he didn't invent the telescope. That's one of those common myths. But he was the first person to use a telescope to point it at the sky. So telescopes were actually invented in the Netherlands and were originally more of a nautical instrument. Think Pirates of the Caribbean and Jack Sparrow with his big telescope, trying to see the flags of other ships at large distances. But they were invented in 1608. 1609, Galileo had the smart idea of pointing at the sky. So he wasn't the person who invented the telescope, but he was the person who invented the astronomical telescope. Now, he discovered a few things that had never been seen before simply by using this new tool. One of them was that he started to see structures on the moon. So when we look at the moon, we can see that it's kind of not a smooth color, but you can't really tell what's going on. We now know that there are lots of craters and mountains, but Galileo was the first person to figure this out. By pointing a telescope at the sky, he was able to see things like shadows in the craters, and he was even able to estimate the height of the mountains using those shadows. In fact, this is a picture of one of the sketches that Galileo made. Another major discovery was that a planet other than the Earth had moons. Now, here we've got Jupiter and those 4 moons that he discovered. We call them the Galilean moons. They are the biggest. And here you can see pictures from his notes. So he's got Jupiter, and there are these 2 other little objects that he can see through his telescope. And then a couple of days later, he can see they've moved. And a couple of days later, they've moved again. And a couple of days later, they've moved again. So these are really Galileo's notes. Now, why is this significant? Well, in the original geocentric model with the Earth in the center, everything orbits the Earth. But this suggested that there was something orbiting something else. And so what he saw would have looked something like this. Over the course of a few days, there are these little blobs and they're moving. They're actually in orbit around the planet, but we see it edge on, so we just see them moving side to side. Again, this was it wasn't direct evidence that the Earth was moving, but it was evidence that there was something that orbited another planet, not just Earth. He also was the first person to see the rings of Saturn. Now, he didn't know they were rings. It took a little while before we figured that out. Here you can see a nice image of how over the course of a year, we see different orientations, just like as we move around the sun, we're moving our orientation towards the sun. We're seeing different orientations of the planet. So sometimes we see the disk edge on and you can hardly see it. And sometimes we see it at an angle so we can see it better. What Galileo really saw was something like this. It was, again, it was this circle, but then it had these two blobby things that he might have called ears or something like that. Simply that there was something else there, that it wasn't just a sphere. And again, this was the importance of this discovery, that there was something there that wasn't a sphere. It wasn't this perfect spherical shape. This is just a quick look at the sketches that Galileo made himself. And here we've got some more of those that are not just Galileo's, but different observations of it over the course of about a century. Galileo also discovered sunspots. So here I've got a drawing of his sunspots. This is actually from the day before, the four that you can see up above. So here I've got, this is in June 1612, and he's got the 24th, 25th, 26th. He's seeing how they're changing, and you can see in detail what they look like. And this is an image of the actual sun and its sunspots. And you can see that his drawings are a pretty good representation of what it looks like. Now, why are sunspots important? Well, along with the mountains on the moon, it basically suggests that they're not perfect spheres. There's this idea that these things are smooth, perfect spheres, but now we're seeing blemishes. We're seeing craters and we're seeing sunspots. I would say that the real big discovery that Galileo made that really was an end to the idea that the Earth was the center of the universe was that he could see the phases of Venus. What do I mean by that? Well, planets have phases just like the moon does for the same reason. Sometimes we can see the whole of it lit up like a full moon. Sometimes we can only see half of it. Sometimes we only see a crescent. What Galileo did was to take a look at what Venus looked like. This is the little symbol for Venus. And sometimes it was a very large crescent. Sometimes it was a smaller crescent, smaller still at half full, smaller still at gibbous, and smallest at full. But he was seeing all of these different phases. Now, to understand how this is such an important piece of evidence, let's look at the ideas around whether the universe is Earth-centered or Sun-centered, and what that would mean for what we should see in terms of the phases of Venus. Here we have how this works in the old Earth-centered system. So here's the Earth in the center, here's the Sun. This is the orbit of Venus. It's deferent, so that's the orbit that Venus actually makes, but it also does this little orbit, and you'll see this when I set the animation going, around on the epicycle. And this allows us to explain how sometimes Venus seems to move in one direction across the sky, and sometimes it appears to go in the other direction. So let's watch this. We've got Venus is going around on this little circle, and that little circle is going around on the big circle. So let's just watch how that works for a second. Now, when we get up here, we can see that when we get to here, and Venus is between us and the sun, we cannot see it. And as it's moving away from the sun, we see a crescent, but we only ever see a small portion of it. We don't ever see it in full phase. We always see a crescent. Now the crescent gets bigger up to almost half full, but then it gets smaller again. And so this is what we should see through a telescope if this is the situation, if this is how the system is actually set up with the Earth stationary and the sun and Venus moving around in this way. So now let's look at the reality of the situation. Here we have the sun, here we have Venus, and here we have Earth. And now we're going to be looking at how it looks as it goes around again. So we can see here that as Venus heads towards the Earth, it's getting smaller and smaller and more crescenty. But as it moves away again, now when it gets over to the other side and it's almost on the other side of the sun, now we can see a full Venus. Just like with the moon, Venus's orbit is not exactly aligned with Earth's, it's a tilt. So we do actually get to see it in all its phases. We can also see how it gets smaller and smaller as it gets up to full phase. And then it gets bigger and bigger again as it gets closer to Earth, but we're only seeing a small portion of it, so we're seeing just a thin crescent. And this matches exactly with the sketches that Galileo made. So we just saw how the phases of Venus work in both the geocentric and heliocentric models. Here, this is the geocentric model with the Earth stationary, the sun is going around the Earth, and Venus is going around in this epicycle that is going around the sun. And you can see here that we always see that crescent phase. Whereas with Venus going around the sun and the Earth going around the sun, we're going to get to see Venus in crescent phase and full phase. And so really what Galileo saw and sketched was showing you that Venus must orbit the sun. He didn't show that the Earth orbited the sun, but he showed that Venus must orbit the sun and therefore not orbit the Earth, which was one of those little chinks in the armor of the geocentric model. So let's get on to Tycho Brahe. Brahe was a Danish astronomer who has some fun stories about him. He was a nobleman. He lost his nose in a duel. He would sometimes see pictures of him with a little cover over his nose. And he died when his bladder burst because he was being too polite to leave the king's table. And eventually, you know, his bladder said, no, I'm not having this. Okay, but what did he do for astronomy? Tycho was the person who made lots and lots of amazing observations of the sky. He had great charts of where the stars are, and he observed the planets so that he could see how they were moving across the sky. And this allowed him to make predictions like, here's the star here, and the next day it's here, sorry, planet's here, the next day it's here, the next day it's here, and the planet is moving, and so you can say, okay, it's going to be over here next. And so that's really important. He also discovered a new star, a nova, and that was something that really helped him to break away from Aristotle's model of perfection. So in the idea of geocentric model, everything is perfect and spherical and unchanging. And in seeing a new star pop up, that meant that the sky could change. Actually, it was a star that got brighter. So it was always there, but it was too faint to see. It got brighter and we were able to see it. But he didn't see the parallax that he expected to see in order to show that the Earth was moving. Just like Aristotle, he thought that he should see evidence of the Earth's motion in the stars closer to us being slightly shifted as the Earth moves. So I can demonstrate this briefly. If you hold your finger up in front of your face, close one eye and notice what is behind it. Then switch eyes to the other side and notice that your finger seems to have shifted relative to what's behind it. That's the idea of parallax. The Earth moves around the sun, and so on one side of the sun, we're looking in one direction slightly, and as we move around, we're looking in a different direction. And so 6 months apart, we should see the stars shift. We actually do, but the shift is so small because the stars are so far away that you cannot see it without a telescope. So Tycho did not see this evidence. So he had an interesting model for how things worked that was kind of a mishmash of heliocentric and geocentric. But the Earth was still stationary. And that brings us to Johannes Kepler. Kepler was someone who doesn't get enough credit, in my opinion. Kepler was an assistant to Brahe. He had access to all of his observations, so he knows exactly where the planets are observed to be. And so what he did was to take that and build a new model. He expanded on Copernicus's sun-centered model, but instead of having the orbits all perfect circles and moving at constant speed, he abandoned that. And he said, no, let's make the orbits ellipses. So it's an elliptical path. An ellipse is a circle that's kind of stretched out. We'll get into that a little more in a second. He also said, let's not have uniform velocities. Let's have the speeds of the planets changing as they move around the sun. So let's get into this. We're going to start with Kepler's first law. The first law is the orbits of the planets are ellipses with the sun at one focus. Well, before we can do that, we need to talk about what is an ellipse. So here I've got a diagram, and this is a piece of string that is tied so that it is just a loop. You've got a pin in two places, and then you hook the loop over that, and you pull it taut. So the distance from this pin to the pencil and back to this pin stays constant. It's set by the string. And so as you pull it taut and draw around, you're going to get an ellipse. So instead of being circular and with a radius, we now have different distances from the center. And we have a long axis, which we call the major axis, and a short axis, which we call the minor axis. And these places where we put the pins in are the foci or focuses. Just to get in a little deeper, here's the center of the ellipse, and here is the focus. The distance from the center to the focus, that kind of determines how stretched out it is. The closer the focus is to the center, the more circular it is, the further away, the more like a straight line it is. And so this relationship between how stretched out the focus is, how far away the focus is from the center, and how stretched out the ellipse is called the eccentricity. The more eccentric the ellipse is, The straighter it is, the more close to a straight line it is. The smaller it is, down to 0, you get a circle. Let's look at that a little more closely. So here I've got an eccentricity of 0. It is just a circle. The focuses are in the center. Here I've got something where the focuses are pulled out a little way. And so now we've got something that's a little bit stretched out. And now we've got something with the focuses pulled out much further. And that is a much more eccentric thing. If you keep going, you'll get a straight line. Let's look at this in a little more detail. So here I've got a circle. Both focuses are in the middle where that X is. But now we're going to stretch it out. So we're pulling one of the focuses away. And what we're seeing is that it gets more stretched out until we get to a very eccentric thing. And now the eccentricity is going back down and it's getting more and more circular. So let's come back to the first law. The orbits of the planets are ellipses with the sun at one focus. So here's the sun at one focus. This is exaggerated. None of the planets have elliptical orbits that are this stretched out. And the point where the planet is closest to the sun, that's called perihelion. Peri for close and helio is the sun. And the other side of the orbit, when the sun is at this focus and now the planet is furthest away, that is called aphelion. And we can work out what the difference is between the aphelion and the perihelion using the semi-major axis and the eccentricity. Remember, the semi-major axis is the distance from the to the edge, but it's also the average distance from the sun to the orbit. Okay, so it's much shorter here and much longer here, but on average, it's just the semi-major axis. Just to emphasize this a bit more, the sun is at one focus. The closest point is called perihelion. The furthest point is called aphelion. There is nothing at this focus. Let's move on to the second law. In the second law, the line from a planet to the sun sweeps out equal areas in equal intervals of time. This is much easier to see if I show you as an animation. So here I've got the sun, here's a planet, it's got an elliptical orbit, and we're going to watch what happens. You can see as it's moving around, it draws out kind of a triangle, a segment that's a certain length. Now you can see it's slowing down as it's moving to this end of the orbit. And so when we get over here to aphelion, we're going to draw another one that takes the same amount of time to go along a bit of arc here. And you can see here, it took the same amount of time to do this as it took to do this. And again, here we've got the same amount of time to do this. Let's do this one and this one. Okay. Let's just watch it again. And as it goes around, that has an obvious consequence. If this has got to be an equal area to this one, then it covers a much more of an arc along the orbit when it's close to perihelion than it does when it's close to aphelion. And that means that it's moving much faster at this end of the orbit than it is at this end of the orbit. So remember that Kepler dropped the idea of uniform motion, that the speed of the planet stayed the same all the way around, but he has rules. It's going to be fastest when you're closer in and slowest when you're further away. So this is just a static image of that. And this is, say, over the course of a month close to perihelion, and the Earth is at perihelion in January. So over the course of January, it doesn't take that much time for us to get past perihelion. This is 30 days. This is how long it takes. This is 30 days of time. It gets from quite away from the perihelion to quite a way past the perihelion. But at aphelion, it's moving much more slowly. So it takes so it's much closer to aphelion in the time that it covers that 1 month period. Okay, let's get into Kepler's third law. Kepler's third law says the squares of the orbital periods of the planets about the sun are proportional to the cubes of the orbital semi-major axes. Okay, that's a lot of words. What it means is that the time it takes to go around on its orbit is related to its distance, but it's not a nice simple linear relationship. So we have to use a square and a cube. This is if you work in the right unit. So this is always true, but depending on the units, you might have to put in some sort of constant to do the conversion. But if you work in years for the period, the time it takes for the orbit to happen, and the semi-major axis in AU, that's astronomical units, that's the average distance of the Earth from the sun, well, then this works exactly. You're going to get, if you know how far away a planet is, you can work out how long it takes to go around and vice versa. So that means we can look at what the average speeds are. If we know how long it takes to go around and we know how far away it is, we know how long its path is, we know what its average speed is. And here we can see that Mercury is moving pretty fast. As we come to Venus, it's a bit slower, Earth is a bit slower still, and so on. And so what we're getting is that the further away something is from the sun, the faster it's moving. So let's summarize those three laws. Kepler's first law is that the orbits of the planets are ellipses with the sun at one focus. Second law, the line that connects the planets to the sun sweeps out equal areas and equal times. 3, the squares of the orbital periods of the planets about the sun are proportional to the cubes of the orbital semi-major axes. And again, all of these put together make a neat way of looking at where all the planets are and being able to make predictions of where they're going to be in the future or where they were in the past. And that's really important. And that's why this works when Copernicus's perfectly circular model did not. So let's summarize the Renaissance astronomy. So here we've got from 1543, when Copernicus died, through to 1642, we've got Tycho doing lots and lots of observations, Galileo using a telescope, here's where the telescope was invented, and Kepler being hired by Tycho and using his observations to come up with his laws. And all of this happened around the time of Shakespeare, and this is a really important time that really birthed modern astronomy.